Hi, in this video we're going to be discussing the squeeze theorem, sometimes called the sandwich theorem. Sandwiches. In this situation, we're given an unknown function, g of x. Now, it could be a known function, but just something that's really ugly. So it could be unknown or just plain ugly that we don't know anything about it. So, and we're told this statement right here. Now, earlier in another video, we said that this statement means we are between. So in other words, we're saying that g is between h of x and f of x. So let's look at the graph below. So what could we assume about the value of g of 2? Well, since g is always going to be between f and h, where f and h meet, we should assume that they all meet at the same place. So we could assume that g of 2 has to equal 3. Now, how can we prove it? This is called the squeeze theorem. Now, the first thing you have to do, kind of like IVT, is you have to mention that h of x and f of x are continuous. You need to establish the following relationship and solve. Now, notice, we're using limits. And the reason we have to use limits is because g of x, the middle function, is unknown. We don't know anything about it. It could be that the value doesn't exist at 2. There could be a hole there. There could be something causing it to not have a value there. So we use limits to say, well, we're just going to approach it instead. Next, write your explanation, and don't forget to mention continuity. So let's take a look at an example. Let f of x equal 3x, and h of x equal this x cubed plus 2. And we're told that g, whoops, that should definitely be an h right there. And we're told that g is between f and h. So we are between here. Use the squeeze theorem to find out what happens as g approaches 1. Now remember, we don't know anything about this. We are into the unknown. We don't know anything about it except that g is between f and h. So to start this, we have to establish that f and h are continuous. And that's easy enough to do. We can say that yes. Step 1, f of x and g of x are continuous. There's no domains. We can just say they are continuous. Now, the next step, we have to establish the limits. Okay? I'm going to take the limits of the outside. So what I want to do is this. The limit as x approaches 1 of 3x is less than the limit as x approaches 1 of my unknown, which has to be less than or equal than the limit as x approaches 1 of my other outside function, x cubed plus 2. And then I can just plug in. Well, here I get 3 is less than or equal to the limit as x approaches 1 of g of x. And if I plug 1 in here, I also get 3. So what is this telling us? Even though I don't know anything about g of x, it's going to be between 3 and 3. Well, what's the only number you can think of that's between 3 and 3? And of course, the answer is 3. So we're going to say, therefore, the limit as x approaches 1 of g of x has to equal 3. And there's our answer. That's the squeeze theorem. Very easy, but if you don't do this, I don't read that. So try number 2 on your own real quick. Use the squeeze theorem to evaluate the limit of g of x, if g of x is unknown, and we're given our little rule right here, 9 minus x squared, that g is between 9 minus x squared and 9 plus x squared. And we want to find out what's happening at we approach c, but they're telling us c is 0. And we can define f and h as those two functions. So step 1, we're going to say, okay, f of x and g of x, sorry, not g, they used h, and h of x are continuous. Now, if you notice, we didn't really care much about g being continuous because we don't know anything about it. Step 2, establish your limits. The limit as x approaches 0, remember we're using 0 for c, of 9 minus x squared, less than or equal to the limit as x approaches 0 of g of x, which is less than or equal to the limit as x approaches 0 of 9 plus x squared. Plugging in 0, we get 9, less than or equal to our limit here. Plugging in the 0 here, we also get 9. And if you notice, voila, some beautiful things happen. Look at this. We're going to be between 9 and 9. So yeah, so therefore we can say that the limit as x approaches 0 of g of x has to just equal 9 right there. Very easy to do. Please don't forget continuity. All right, let's look at some AP questions. Let f be continuous on this closed interval, -3 to 6. We're told the value at -3 is 1 and the value at 6 is 3. Right away, I'm thinking intermediate value theorem. Anytime they give me two values at endpoints, I'm thinking, oh, look, there it says IVT. I'm thinking IVT. So they're saying IVT guarantees the following. Now, the first one says f prime of c. Now, for those of you who've already seen a lot of this before, that's a derivative. Well, since we haven't done derivatives yet, that's probably not our choice. The next one says all the y, that it has to have all y values between -1 and 3 for all x. So in other words, it's going to take on all y values between -1 and 3 for all x values between -3 and 6. So if I think about what this graph looks like, between -3 and 6, and we're told that the y values go from -1 all the way to 3, right here. It's continuous, so I got to draw that being a continuous graph. So this says it's going to take on all y values between -1 and 3 for all x values between -3 and 6. Well, that's true. This one says the value of c has to be 1 for at least one c between here, between -3 and 6. So, real quickly, let's see here. I messed up on B, so I'm going to go back and fix that with you. So for B, this is saying that all the y values have to be between -1 and 3. Well, not necessarily. We just know the start and end point. I'm starting down here and I'm ending up here. The graph could look something like this. I only know where we start and where we end. We can't guarantee anything outside of that range right here. So that can't work. The next one says that the value of c has to be 1. That's the only one that works, because 1 is between -1 and 3. So this is saying any y value, that the y values just only can be between -1 and 3. But I can clearly have a function looking like this. All right, the next one talks about a table. The table below is a measure of speed at which Mr. Wernow drives to school at various times. Use it to answer the following questions. So the first one says, what is the least number of times Mr. Wernow's speed was 28 miles per hour? So let's read this real quickly. 28. Well, here's a time when I crossed 28. So I'm looking for that betweenness. This is our IVT. I'm looking for that betweenness. So there's once I have to cross 28. There's another one I have to cross 20. I can't go from 30 to 15 without crossing 28. Keep going. There's another time. Here's another time. Here's another time. And over here, here's another time. So I'm looking for that betweenness. Is 28 between 30 and 26? Yeah. So the answer here would be 1, 2, 3, 4, 5, 6. So it's a minimum. We say it's a least because we can't get, there could be more, we just don't know. We only know these times. What is the least number of times his speed was 17? So let me go ahead and erase all of those, and I can answer that. Whoops. I wanted that 6 here. There we go. 17, I go here. No, can't guarantee. Looks like right here. crossing 17 here. And look, doesn't look like it crossed any more times, so this would be 2 times. Now explain how we know. Well, this is the IVT. 17 is between 15 and 30, and 17 is also between 15 and 25. So I can use that. And this is going to be a continuous function. When you're driving, it's a continuous function. Must there have been a time when the speed was 60? Well, looking at the graph, we don't know. This is an I don't know. We can't guarantee. So we just say this can't be guaranteed with IVT. It could be. We just have to use another tool for it. All right. Hope you enjoyed the videos. I'll see you soon. Bye-bye.